So for this AP question, we have three spheres that are sprayed into a chamber and become charged. And we know that their charges are plus 3e, plus 5e, and negative 3e, where e is that fundamental charge there, the charge of an electron. And then they collide and separate, and so they have the possibility of exchanging charges between them, and we want to know which of the following are possible values for the final charges on the three spheres. So two things we want to keep in mind here. Number one, charge is conserved, and number two, charge is quantized. So let's think about that conservation of charge piece. Initially we have plus 3e, plus 5e, and minus 3e for a total of plus 5e. So that's how much charge we start with, and that's how much charge we need to end with. So if we look at our possibilities here, for our three arrangements, this first one, plus 4e, minus 4e, and plus 5e, that results in a total charge of plus 5e, so that works. This second one here, we end up with negative 4e plus 4.5e plus 4.5e. That also gives us a charge of plus 5e, so that one works. This third one here is going to end up giving us a charge of plus 4e, so C is no good. And for D, we're going to end up with a charge of plus 5e as well. The other thing we have to keep in mind here is charge is quantized, and the smallest possible unit of charge is E. We can't have part of that fundamental charge. So we see here for B, we have half an E. So that also is not possible, which means the only two remaining are A and D. So those are going to be our two correct answers here. Okay, so we have an experimental design question here, and we're tasked with two questions. We want to know whether or not in 1 second fewer electrons leave a bulb than enter it. That is a bulb connected to a resistor in a circuit. Okay, that's the setup they give us. And the second question is, does the electric potential energy change while the electrons are inside the bulb? So what I'm going to look at is I'm going to first draw my diagram here for my setup, because I think that's going to make it easier to explain what it is, and we're supposed to draw our diagram anyway. So I'm going to start out by drawing our diagram. So first we're going to have our power source, power supply here, and we need to connect it with a resistor. Okay, and we need to connect that with a bulb. Looks something like that. Okay, now we want to see whether or not fewer electrons enter the bulb than leave the bulb. So how exactly are we going to measure that? Well, we're going to measure that using an ammeter. So what I need to do is I need to put an ammeter in my circuit. Remember, ammeters always go in series. We want to know about entering the bulb and leaving the bulb. So I'm going to put an ammeter on both sides of my bulb. Alright, so now I have an ammeter in series with my bulb on either side. The other thing I want to do is think about the electric potential energy. So to measure that, I need a voltmeter. That's going to measure the electric potential. That represents the energy of the electrons as they're flowing through the circuit. So how am I going to answer these questions? First, I'm going to construct the circuit shown in the diagram. Okay. So I'm going to connect the three basic elements in series. I'm then going to place an ammeter in series before and after the bulb. And I'm going to place a voltmeter in parallel across the bulb. And the last thing, and this is the completed trial piece, I'm going to turn on the circuit, all right, so that we can get readings of our current and our voltage. All right, for part B, we want to explain how this data is going to help answer those two questions. That first question was, we want to know whether or not fewer electrons enter the bulb than leave the bulb. So for that first question, we're going to compare our ammeter readings. Okay, and the ammeter measures current, which is really a measure of the flow of electrons. So if those ammeter readings are the same, it means that the same number of electrons enter and leave. If they're different, it means a different number enter and leave. For question 2, we're going to look at our voltmeter. That's going to help us determine whether or not the electric potential energy changed going across the bulb. And if that reading is not 0, right, a reading of 0 would indicate no change in electric potential or electric potential energy. So if that reading is not 0, that means that there is a change. They lose some potential difference. All right, moving on to part C here. We want to know whether or not we can use this setup to determine if a light bulb is non-ohmic. Okay, so that means, we talked about this in class, that non-ohmic means the resistance changes as the current changes. So, do we need to modify our setup to part A? And the answer is no modification needed. All right, although you could modify it, you could remove the resistor. We really don't need any modification. We also could remove one of the ammeters, but again, that's really not needed. So what additional information would we need to collect? We would need to vary the voltage of the power supply so that the voltage and therefore current across the bulb varied. And then we're going to record those voltage and current readings. All right. Lastly, we want to know how we can use this data, and I think the easiest way to do this is to graph voltage versus current. All right. If that graph is linear, then we know it's an ohmic device. If it's not, it's a non-ohmic device. The second part of this question is asking about how the uncertainty in the voltmeter and ammeter would affect the argument for concluding whether or not the resistor is ohmic. There's lots of things we could do in terms of data analysis, but the key is to know that the line might not be perfectly linear. Okay, so taking additional data will help us get a clearer picture of whether or not it is ohmic. Alright, so we're going to go ahead here and take a look at this circuit, and the first question we're asked to do is we're asked to rank the magnitude of the potential difference across each resistor from least to greatest. The first thing I see here, we know that all these resistors are identical, is that B is equal to C. I know that for sure because these two, B and C, are connected in parallel, so they must have the same potential difference. Now I'm going to go ahead and think about A and D, okay? And I could do a little bit more mathematical proof of this, but here's what I know. I know that B and C collectively will have half as much resistance if I were to combine them, okay, into a single resistor. Okay, I know they'll have half as much resistance as the other two resistors, which are identical, okay, combining them in parallel. So that means, all right, knowing that all of these resistors get the exact same current when we reduce this circuit partially, that means that these two resistors, okay, will get more voltage than B and C, all right, and they're also going to get a voltage that's equal to each other because they both get the full current of the circuit. They have the same resistance, so they're going to get the full voltage. So that means that my final ranking is going to be A equals D, which is greater than B equals C. To explain this, all right, real quick, I'm going to say that B and C are in parallel, so they have to get the same voltage. All right, so that's why those two are equal. A and D in series get the same current, all right, and since they're the same resistance, they must be equal. And then the last point is that A and D, all right, we could have thought about it this way too, get the full current of the circuit, okay, so they have more voltage across them, more electric potential. Okay, moving on to part B here, we're going to remove resistor B from the circuit, and we want to think about whether or not the current through A increases, decreases, or remains the same. So you might be tempted to think, oh, well, there's now less resistance in our circuit. That means the current through A must increase, okay? But actually what happens is having these two in parallel like this actually was less resistance. Like I said before, they combine to be a resistance of 1/2 R. When we remove it, now we get the full resistance of C. So here, our total resistance would have been 2.5 R, whatever the resistance of a single one is. Now it's gone up to 3R. So that means the current through A is actually going to decrease. All right, and the important points we need to hit on here. The first thing is removing B increases the total resistance of the circuit. When that happens, it decreases the total current of the circuit, which all goes through A. That full current goes through A, so it ultimately ends up decreasing. Okay. For the last one, when resistor B is removed, does the current through resistor C increase, decrease, or remain the same? So for this one, we're in kind of a weird situation if we're thinking just about the flow of current. All right, and here's why. The total current through the circuit decreased. So because of that, we might be tempted to say the current through C decreased. But on the same token, all right, by removing B, C now gets the full current, whereas before it had to share the current with B. So for that reason, I might want to say it increases. I think the easiest way to think about this is in terms of electric potential, actually. In this situation here, since all three are identical, C is going to get 1/3 of that total voltage of the battery. In our original circuit, though, A and D actually got more of the voltage. Okay, B and C combined to be half the resistance, so they actually got less voltage than A and D, and each one of them got that voltage. So before, C got less than 1/3 of the share. Now C gets 1/3 of the voltage. And that to me is the easiest way of thinking about it. Sometimes thinking about the current is tough because there's two things at play there. But the voltage definitely goes up, which means the current ultimately increases. So my explanation, I would say that C now gets 1/3 of the voltage of the battery. And since the voltage increases, that means the current must also increase. All right, moving on to this problem here. We have three circuits that are shown here with combinations of either one or two bulbs connected in either series or parallel. If we look real quick, circuit 1 just has bulb A there, just as a single bulb. In circuit 2, if we look closely, we see that those bulbs are connected in series. So that means that our circuit would look something like this, with B and C connected in series with each other. And then finally, if we look at the last circuit there, we see how they're connected in parallel. The current can either go through D or go around and go through E. So that means that that final circuit has two bulbs, D and E, connected in parallel. So the first thing we want to do for part A is we want to rank the magnitude of the potential difference across light bulbs A, B, C, D, and E from largest to smallest. Okay, and if we think about it, they all have the same battery. They're all identical bulbs. A is going to get the full voltage of the battery, as will D and E, because in those circuits, completing each loop, it's the only bulb that you cross. So that means that A is equal to D is equal to E, and they're going to be greater than B and C, which will get half the voltage of the battery. Now we know it splits evenly because they're identical. Okay, and so that's going to be our ranking there. In terms of an explanation, I would start by saying that bulb A gets the full voltage of the battery. It's the only bulb in that circuit. D and E will also get that full voltage because each one is on a different loop. Therefore, they will be equal to the voltage of the battery. B and C, on the other hand, they're on the same loop, and so they're going to split the voltage because they're identical. Each one will get half the voltage of the battery. For the second part, we want to know which circuit will the battery run out of usable energy first, and in which circuit will the battery run out of usable energy last. We're going to do a full paragraph explanation, but thinking about this quickly, we want to think about power. Okay, power is the rate at which energy gets used. Power is equal to voltage times current. And so they all have the same voltage, so the one that draws the most current will ultimately run out of usable energy first. That is going to be circuit 3, because it has the lowest resistance. And which one will run out of usable energy last? The one that draws the least current, so that will be circuit 2. In terms of an explanation here, I'd start by saying that power represents the rate at which energy is used. And power is going to be directly proportional to both voltage and current. However, in this case, all three batteries have the same voltage, which means that what really matters is the current. So, in terms of current, we're going to think for a second about resistance. Circuit 3 is going to have less resistance than circuit A because adding a bulb in parallel decreases the resistance of the circuit, and therefore the current will be the most in that case because current and resistance are inversely proportional for a constant voltage. Circuit 2 will have the most resistance because adding a resistor in series will increase the resistance, and therefore circuit 2 will have the least current. So that means that circuit 2, which has the least current, will also use energy up at the slowest rate. It will have the lowest power, and therefore that battery will run out of energy last. Circuit 3, which draws the most current, will use up energy at the greatest rate because it has the highest power, and that circuit will run out of energy first.